Cool. Hello, everybody. Welcome to our nice 116th international talk. We are 2 minutes late due to setting some online streaming platforms, but I think we are still right on time. Today, we are honored to have Professor Lin Yao from University of South Florida to talk about some very interesting topics. Do LLMs have geospatial intelligence, exploring their abilities in localization, hazard reasoning, and event simulation? Professor Lin Yao is assistant professor in School of Information at the University of South Florida. Previously, he was a postdoc at the University of Michigan and obtained his PhD at the University of Maryland. His current research is mainly focused on human-centered AI, AI agent, urban computing, and health informatics. And I am today's host. My name is Hao Lun. I'm a final year PhD student at Milan and McGill University. So without further ado, let's welcome Lin Yao to talk about this interesting talk.
Hi, Holun. Thank you so much for the invitation and for the introduction of me. I'm super honored to have this great opportunity to share my work with everybody. And at the start, I really want to briefly introduce the concept of word models. I know this is not a new concept for the AI community. I want to quote Dr. Fei-Fei Li's comments mentioning that from words to votes, spatial intelligence is AI's next frontier to kick off my session. So right now, the state-of-the-art AI agents do have the ability to learn from the historical observation and taking the real-time feedback from the real world, and then make prediction and simulation that can guide the decision-making process in the real-world events. So word models are the ones that can understand the dynamics of the real world, including the physics and spatial properties. And this also enables large language model to simulate realistic cause and effect scenarios. So my key takeaway from this is that the advanced AI agents, they do have the ability to understand the physics and the spatial properties. And this motivated me to think about whether large language model could have this geospatial intelligence. As compared to the traditional models, large language models have the following several really obvious advantages. So the first one is the power of multimodality. We all know that the traditional model can just process the numerical information or the image information, then make one prediction. But in the geospatial tasks, a lot of tasks show the data are really heterogeneous data sources. So this requires that the model should have the ability to handle this multimodality of the data resources. And also, large language model can help overcome semantic gaps in conversational models because large language model can understand the semantic and contextual awareness. And also, since the output, it can generate text. So this can help bridge the information and the reasoning process. And by functioning at the word models, and large language model can provide the decision makers some reasoning process, and that can help people understand whether its reasoning, its inference is reliable and consistent. So motivated by this ideal, I have explored the large language model for geospatial intelligence through 3 applications that I will be covering. I will cover in today's presentation. So the first one, we investigate large language models' image geolocalization ability. And for the second one, we test their ability for natural hazard prediction. And the last one, we use large language model to build pipelines to simulate the pre-event human-perceived impacts. And now let's go to the first project. So what is the image geolocalization? Image geolocalization refers to the process, the reverse geocoding process, so that it can infer the geolocation from a given image, especially by understanding the visual cues. So for example, this is an image that I've taken during my postdoc study at University of Michigan, and this is the image taken outside of the law school in Ann Arbor. When I feed this image into large language models, and large language model can return me the analysis of those visual cues. So for example, ChatGPT says, this is the classic United States Midwestern University architecture, especially given the collegiate Gothic stone facade with tall, narrow-rated glass windows. And also it can capture the environment cues, so such as the trees and the foliage during the fall. And also there's a really small sign at the bottom, at the left bottom of the image. That's really hard to identify by our human eyes, right? And then large language model can just detect this blue sign with a big aim that generally represent the University of Michigan logo. So by returning this vision, these visual cues, and large language model returns me that, okay, this is an image where I took outside of the law caught in Ann Arbor. This is really provide really specific latitude and longitude for this location. So guided by this motivation, by this observation, I work with my collaborators and we propose 3 research questions. So the first research question, we are curious to know how do large language model perform on image geolocalization? And for the second research question, we're curious to know whether large language model, whether the performance can vary across different geographic regions. And the last research question, we want to explore large language models reasoning process. So that is, how do large language model use those visual cues when reasoning about the image location? And to do this project, we need to collect some data sets. So we compile 3 data sets. And the first data set, we just randomly sample some images from a publicly available data set compiled by National University of Singapore. So the original data set consists of more than 1 million images covering more than 688 cities worldwide. And we just random sample about like more than 6,000 images across different countries. And this is our first data set. And for the second data set, we choose the Google Map United States point of interest cross-sourcing. So these images are uploaded by the Google Map users. And then we randomly select some point of interest across different states. And then we collect about like 3,000 images for the second data set. Because the first 2 data sets, because all of those images, they are publicly available. So we wonder maybe large language model have seen these images in its training process. So we also collect the third data set. So this is privately collected using our mobile phone. So, and these 3 data sets covers different like environment type, like indoor, outdoor, and scene types, like building, scenery, street, and also different settings like urban, suburban, rural, and natural. So building on these 3 data sets, we then design our research framework. So for the first figure, you can see these are the image distribution. So you can see well these images are taken. And then we design the prompt to prompt large language model to extract those information. The prompt actually consists of 3 major parts. So the first part is the image information. We ask the large language model to extract relevant information from the image, such as the environment, the scene type, and the setting, including like the urban, suburban, rural, or natural. And then we also categorize the reasoning process into 4 parts. So like the landmark recognition, whether large language model can identify the iconic structure or the text signage, like the street sign or business names, or the cultural indicators, or the spatial context, like the geographic context from the image. And then the last part is the reverse geocoding. So we prompt large language model to return how confident large language model is about its judgment, and also return the address, including street, city, state, country, and also the very exact coordinates, the latitude and longitude of the location. So this is our whole research framework. And then based on the extracted information, we also build some measures to measure large language models performance, such as the identification rate, the geographic accuracy, the distance error, and the computational cost. So especially we focus on the geographic accuracy and also the distance error. So for the accuracy, we measure 3 levels: the country accuracy, the state level accuracy, and also the city level accuracy. And then for the distance error, we use the harvesting formula to calculate the great circle distance between the predicted coordinates and the true coordinates. And then based on these measures, we also build 2 regression models to measure the post-hoc feature importance. So one is the logistic regression. So for the logistic regression, seeing the output is either 1 or 0, it's a binary classification. So we consider if a large language model can correctly identify the city level information, and then we consider this as 1. Otherwise, we consider the output is 0. And then for the ridge regression, we just calculate the log distance error between the predicted longitude and latitude and the ground truth longitude and latitude, and then we calculate the log distance error and use that as the y, and then build the ridge regression model to find the feature importance. So these are the 2 regression models that we built in our study. And then here are the results. So this is our major table. And this table shows the benchmark performance across different large language models based on the first and the second dataset. So the first dataset is the global dataset that we just compiled from the National University of Singapore's published dataset. And the second one, the cross-sourcing dataset. So you can see there are several key observations. So the first observation is that we observe most large language models exhibit higher prediction accuracy on the first dataset. So if you check the city accuracy and the between the first and the second dataset, you can observe that the city accuracy is almost like 20% higher than the second dataset. And one very possible explanation is that because the National University of Singapore, they compile the data using the publicable available data set. So it's very likely that large language model have seen some of the images in its training process. But since those cross-sourcing, those Google Map photos, they're uploaded by the Google Map users. So maybe most of those cross-sourced images haven't been seen by large language model. So this could probably explain why the city accuracy is much lower for the second dataset. And the second observation is that we also find that closed-sourced models consistently outperform their open-sourced models. So if you compare the GPT models, Gemini and Llama, so you can observe that, especially like for the first dataset, almost like 20% higher than the open-sourced model. And the last observation, we also observe a very clear scaling trend. So where larger models generally perform better and showing stronger capability in identifying the location. So these are some of the benchmark performance. And then we try to identify how the large language model can predict the latitude or longitude. So this is the benchmark performance on the latitude prediction using the first dataset. And the y-axis shows the ground truth latitude, and the x-axis shows the predicted latitude. And the diagonal line means that if a point falls into the diagonal line, that means a perfect prediction. So the correlation is 1. And the color of the points means the confidence level of the models. So the blue color means that the model is not very confident, and the red color means that the model is super confident. So there are also some interesting observations. So one observation is that if you just check a single model like GPT 4.1, so you can observe that when the model is confident about its output, it's generally correct, like for GPT 4.1, right? So like those red points just falls into the diagonal line. And when the model is not very confident about its output, it's very likely the output could be wrong. So like if we just observe GPT 4.1, we can get the conclusions. But this observation does not align to other models. So for example, like for all three, the O3 model is generally not very confident about its output. So you can see most of the output just in confidence level 1 or 2. And in comparison, Gemini 2.5 Pro is super confident about its output. Nearly all of the output are in confidence level 5. And if you just compare O3 and Gemini 2.5 Pro, you can tell that, okay, the confidence level actually does not mean anything. It's because the city accuracy and the country accuracy between these two models is quite close. Like for all three, the city accuracy is 42%. And for the Gemini 2.5, the city accuracy is 44. So it's quite close. But these two models shows really different confidence levels. And the next benchmark performance is on the latitude prediction for the United States using the cross-sourcing data. So you can see the accuracy is not as good as the first data set. But one very interesting observation is that for this one, the benchmark performance on the longitude prediction. So if you go back to prior to this slide, you can see you can just observe a very clear, very densely cluster in the middle of the figure, right? But for the longitude prediction, there is a cube-like box in the middle, nearly across all the models. So what does this mean? So I think one possible explanation is that because for latitude prediction, generally, the large language model can capture the environment cues. So for example, like in some higher latitude, like in the north part of in the United States, the tree types in the north part and the south part could be quite different. Like the palm tree generally appear in the south part, but but the palm trees do not appear in the north part of the United States. So large language model may capture those environmental cues when identify the location from the image. But for longitude, there's no clear environmental cues for large language model to identify. So when large language model is not very sure about the prediction, so generally just randomly guessing the outputs. So this also explains why for the longitude prediction, you can see the prediction is quite like follow a uniform distribution, right? And these are some explanations we can think about to explain the difference between longitude prediction and the latitude prediction. And the boundary, the cube-like box, the boundary actually is the border of the United States of the longitude in the longitude. And when plotting the geospatial patterns, we also observe some very interesting patterns. So if you just look at the accuracy for each state in the United States, despite like Llama generally just show very low accuracy, but for like Gemini and GPT, the geospatial pattern is really interesting. So the red color means that the accuracy is higher, and the blue color means the accuracy is lower. So you can observe that some specific states like California, Washington, Texas, and Florida and New York. So these 5 states generally show some higher performance than other states. I think one very possible explanation is because these 5 states, they're really densely populated areas. So people take a lot of like pictures of those scenic spots and upload those scenic spots to the website. So large language model probably seeing those images in its training process. But for some less populated areas, like especially in the middle of the United States, you can see the accuracy is pretty low. So maybe large language model cannot identify those location. And the last observation, the last part of this project, we also did some feature importance analysis using the regression model. So for this figure, the x-axis is the log value, so that can measure the importance of the features, and the y-axis is the features ranked by their importance. So you can see nearly across all of the subplots, nearly all of the models strongly favor the urban and outdoor environments while consistently penalizing rural, natural, and indoor scenes. So if an image like taken in some rural place, and then it's very likely large language model cannot identify the location. And regarding the scene type, we also noticed that like the street image tends to provide some stronger localization signals. I think it's probably because like if a picture is taken on street, there might be like some street signs and business names that appeared on the shops. That can help, those textual cues can help large language model to identify the location. But like if the image is a general scenery, then maybe it's really hard, it's really challenging for large language model to correctly identify the location. So these are some of the key takeaways and observations for the first project. And then for the second project, we want to understand whether we can use large language model for wildfire risk prediction. So nearly in every several years, there will be some like big wildfires happen, especially in the western United States, like in California, Oregon, and Washington states. And for example, this is the image shows the wildfire season during the 2020. During 2020, and you can see there are so many wildfires happened at that time, and these wildfires has caused a lot of property damage to the local communities and even costing a lot of loss of lives. So the traditional models generally use the hotspots counts, the fire radiative power statistic, the time series predictors, or machine learning based models to predict the wildfire hazards. But these traditional models also present some challenges, such as they may lack the semantic and contextual awareness, they may provide insufficient generalization ability across different events, and also this provide limited interpretability for the decision makers to understand the decision-making process. So these are some of the challenges that the traditional methods generally face. And for this study, we also choose the 2020 United States, the Western United States wildfire season. And you can see there are some typical wildfires happen during that period, like the August complex, the LNU lightning complex, the ACU lightning complex. So these are the wildfire names happening in some local areas. So we use this wildfire events to test the large language model's ability. And so the research question that we ask in this project is quite direct. So we're just curious to know whether large language model agents can draw on some structured geospatial data from the physical world to support disaster response decisions. And by doing so, we really hope that the agents needs to actively retrieve relevant geospatial evidence at appropriate spatial and temporal scales. And also, the retrieved information has to be represented in a form that large language model can interpret without being overwhelmed by the large tabular data, because we all know that large language model is not very good at processing the numerical data, right? And the last we challenge is that we really feel the system should generate some stable and consistent outputs across days and events, because the wildfire hazard prediction is a continuous process. We need to predict the hazards every day during the study period. So it's like a cumulative and a temporal prediction. And then to investigate the large language model's ability, we designed this research framework. So when a wildfire event happens, we firstly use the location. And so we can get the location and the data information, especially the fire hotspots from the satellites, right? And then based on the fire hotspots, we create the geospatial awareness layer. So this geospatial awareness layer can take the fire hotspots and then use some function to construct a file convex hull. And then based on the convex hull, we can design the SQL query to query some relevant geospatial information from the database, from the post-GIS database. So including the infrastructure information, demographic information, terrain information, and weather information. So these are some of the very important information that we'd like to feed the large language model. And then because this information, they might be in different granularity. So we also unify the granularity of this information and then write a perception script, and then with the RAG and chain of thought method, and then feed all of this information into the LLM agent, and then predict the daily personnel involved in the rescue efforts and also the daily cost. So these two are the output metrics of our study. And then a key design of the geo-awareness layer is actually consists of 3 parts. Given the limited time of the presentation, so I didn't put a formula of different parts. I just briefly introduced the design concepts of these 3 parts. So basically, it firstly can identify the event and change the wildfire points into, and use the wildfire coordinates and the date, and use the convex hull to standardize the event footprints, and then save the wildfire data in the post-GIS. And then based on the saved data, we can retrieve relevant information from the GIS database. So this includes like the file hotspots and stations, and like the station density, the intraday hotspot counts, and etc. And also we retrieve the demographics information from the database, such as the population density, and also some terrain information, such as the land cover composition, channel diversity, classification of the vegetation, and also the weather information, such as the wind speed and the air temperature. So all of the information retrieval is guided by prior literature that predict wildfire hazards. And after the information retrieved, we also designed the feature consolidation part to unify the granularity of these features, and then save those features into and align these features with the wildfire clusters. And then based on this design, and here are the results. So the first figure show the file impact prediction. So you can see there are a lot of like 5 points. So these 5 points, we get this information from the remote sensing technology. And also the color means the RMSE value. So this is a cumulative. Actually, this figure just shows the cumulative results over the study period. The study period is in 2020 from during September to October is like about 30 days. And so you can see the prediction for different wildfires happened during the study period. And then here is the daily personnel prediction over the study period. So you can see the y-axis is the daily personnel in hundreds, and the x-axis is the study period. It's from August to September. And then the blue dotted line shows the predicted value, and the red dotted line shows the actual value. So, and the area between these two lines show the prediction error. So you can see without the geo-awareness layer, so that means we don't feed the large language model with necessary geospatial information, the prediction is actually quite bad, right? Because you can see the area is pretty huge. And then we feed the geospatial information into large language model. The prediction shows a huge improvement. So you can see the actual line and the predicted line is quite close to each other over the study period. So based on this observation, we can conclude that actually the geospatial, the geo-awareness layer can enhance the robustness for complex files, but the level of improvement can vary across different wildfire events. So for example, like for the cost prediction, so you can see like for this wildfire, the CZU wildfire, so the first four shows the prediction without the geospatial awareness layer, and the bottom four figures shows the prediction with the geospatial awareness layer. So you can see actually for the CZU wildfire event, the prediction shows some improvement. But for this one, for the SCU, especially using the GPT-5 as the backbone model, the prediction actually does not show a huge improvement as compared to that prediction without the geospatial information. And here is the results across different models. And we also actually do a comparison between using large language model and the traditional, like the physical wildfire models, and also the machine learning models, such as using the long short-term memory models. So you can observe that actually the large language model, especially those reasoning models, such as GPT-03 mini and GPT-03, it actually shows a huge improvement as compared to the machine learning model. And the traditional physical model also did a very good job. And the best model that we find across all of these models, one is the GPT-03 mini. So you can see like for 03 mini, the MAE and the RMSE is quite smaller than other models. And the other one that we found the performance is quite outstanding, the GPT-5 mini. Also, the performance is quite consistent across all the 5 wildfire events. And this is the daily cost prediction. Also, like GPT-03 mini and GPT-5 mini, they show some better performance as compared to other models. And next, we also did a feature importance because for the geospatial awareness layer, we retrieve different types of information from the GIS database, such as the weather, resource, containment, infrastructure, demographics, and terrain. And like for the daily personnel prediction, we found that the terrain attributes actually plays the most important feature in contributing to the successful prediction. But for the daily cost, we found that it's really model dependent. So like GPT-5 mini still like labels like terrain as the most important the factor, but for other models such as like GPT-03, so you can see the variance actually, the weight is quite more evenly distributed across these features. So these are some of the key observations for the second project. And for the last project, we try to use large language model for some sudden onset pre-event impact simulation. So we choose earthquakes as the study objects. So the conventional earthquake impact assessment, such as the remote sensing, on-site investigation, and survey response. So remote sensing actually takes the satellite or aircraft based sensors and take some images from the air and then use some computer vision technology to identify the impact. And then for on-site investigation, generally just deploy the 3D scanner or some expert investigation, but it could require like days to weeks deploying the equipment and getting the result. And the last one, the survey response. So survey response, one of the most commonly survey in the United States is the Did You Field Map. So after the earthquake happened, people can log into the system and then fill the survey by filling the information such as how they observe their surroundings, how they feel about the shaking level from the earthquake. But all of those traditional methods, they are actually just do the impact assessment of the event happen. And for some earthquake, especially like for earthquake, because it's happened all of a sudden, it's very different from like hurricane or wildfire or other geospatial events. Earthquake just happened all of a sudden. It's really hard to do pre-event simulation. So the most popular applied methods for pre-event simulation is the ground motion models. But ground motion models cannot identify how people might perceive the risks. Like for the Did You Field Map, actually this is really human centered. This just describes how people feel about the earthquake in a place. So driven by this ideal, we are really curious to test whether large language model can simulate how humans perceive the risks before an event occurs. So based on this ideal, we try to build different agents. Like for each agent, for example, we feed the simulated agent a lot of like information in that place. So for example, like where this person might live, like the geolocation information, like the city, the coordinates, the distance from the epicenter, the geospatial features, like the VS30. So VS30 is used to measure the site condition, which is a very key geospatial feature to predict the seismic risk. And also the socioeconomic and demographic factors like the population density, the housing income, and also like the building features, and also the street view images. We feed all of this information into the simulated agents and trying to prompt the agent to output a simulated value for how the agent might perceive the seismic risks. And before I dive into the results, I want to introduce some backgrounds about about how we estimate the seismic impact. So one of the most commonly used scale, the modified mechanical intensity scale, it consists of 12 levels, estimating how people feel about the shaking. Like level 1 means people cannot feel the shaking, and like level 10, people can feel extreme shaking. So we use this modified mechanical intensity scale to indicate how people feel about the shaking levels during the earthquake. And then for the study, we choose two data sets. So one data set is for the 2019 Ridgecrest earthquake, and the magnitude of this earthquake is 7.1, and the epicenter is located in the Ridgecrest, California. And the other case that we choose for this study is 2015 Napa earthquake. It also happens in California, but the magnitude is a little bit lower. So the magnitude for the 2015 Napa earthquake is 6.8. But the interesting thing is that although the magnitude of 2019 Ridgecrest earthquake is much higher than the other earthquake, but the damage that the earthquake caused to the local communities, to the local areas, is much smaller compared to the other earthquake. One of the reasons is because the earthquake happened in a place where the population density is very small. So most people they live in Los Angeles or the or like the Santa Cruz, they're not affected. They can feel the earthquake, but they're not physically. They can feel the earthquake, but they do not observe many damages in their surroundings. So we feel these two earthquakes could be really representative for our study because you can see, although one earthquake is the magnitude is higher, the damage is actually much lower. So we want to test whether large language model can capture this impact if we just simulate the agents. So, and then we design the research framework. So for the first step, we randomly select some data samples. We use the stratified samples for each zip code. So for each zip code, we randomly generate like 50 samples. And for each sample, you can consider it as an agent, as a sensor that can sense the earthquake happened. As a person sensor that can sense the earthquake happened. And then for the second step, we just feed each sensor with different attributes, so such as the earthquake parameters, like including the epicenter, the magnitude, and the depth of the earthquake, and also some geospatial features like the site condition and the location, like the zip code, location, distance, and also the building types, and also the socioeconomic factors, including the population density, the age, the income, and education, and last is the street view images. So you can see there are multiple types of data that can fit into each sensor. And then we also design the prompt engineering and then design the experiment, including like the model selection, prompt techniques, ablation study, and the performance evaluation. And then for the evaluation metrics, we firstly calculate the average estimation using all of the simulated sensors in a zip code area. And then we can calculate the average estimate for given the zip code or county level. And then we use the root mean square error to calculate the difference between the predicted value and the ground truth value. And last, we also use the correlation coefficient to see how the predicted value, how the trend of the predicted value aligns well with the ground truth value. So these are some of the evaluation metrics that we use in this study. So here are the results. So this is the simulation results for the 2015 Napa earthquake. So you can observe that so the star sign means the epicenter of the earthquake. And so you can observe that for area that close to the epicenter, especially for those several counties close to the epicenter, they experience some heavier impact and the level 7 the seismic impact. And then for counties that further from the epicenter, you can see the MMI, the predicted MMI is much lower. So you can see the color is actually lighter. And this is the simulation result for the 2019 Ridgecrest earthquake. So you can see the epicenter is far from the densely populated areas, and then the damage close to the epicenter is really heavy. And then for areas that farther from the epicenter the damage is much smaller. So this is the simulation for the 2019 Ridgecrest earthquake. So you can clearly tell the difference by comparing these two maps, right? And then I think one very interesting observation when we do the experiment is we are also curious to know, is it possible that large language model just learn the information? So actually we did several data leakage tests. So one data leakage test is we set the earthquake happen time in the future, not in the past. And then we also hide the location of the epicenter. So large language model does know where the earthquake happened. But we found the simulation results is also very similar to the simulation results. So like for table 3, so you can see this is the experiment results on data leakage. So for the right-hand side, it showed the simulation without the location information. And for the result on the left-hand side, showed the simulation result with the location information. But you can see the simulation result is quite similar to each other. And then across different models, we also have several interesting observations. So one interesting observation is that like for the first, 2014 Napa earthquake, we observed that Qianwen 2.5 32 billion model generate the best prediction performance. But GPT-4o at the time of the experiment generate the highest correlation. But one very interesting thing that the higher RMSE does not always result in higher correlation, and also higher correlation might not result in higher RMSE. This observation is quite interesting because sometimes we find the overall prediction could be deviated from the ground truth values, but large language model can actually capture the comparison, especially the comparative relationship between different places. So this can explain why sometimes the RMCC higher, but the correlation is actually not that high. And this is the city level simulation results for different cities using different large language models. So you can see this is the actual average MMI, and these are the predicted MMI by large language models. And these are the the count of the sensors that we randomly generate for each city. So this is the pre-simulation performance for the city level simulation. And okay, so based on these three projects, I want to summarize some key findings. So like for the first project, the image geolocalization, we actually observed that co-source models always lead in the performance, but also at a higher cost. And models rely on different visual cues, but they might not generate a holistic understanding. And for the second model, we find that, okay, by feeding large language model with the geospatial information, that can help large language model to outperform both physical and machine learning baselines. And we also found the integration of the spatial and temporal cues within the geospatial awareness layer can improve the prediction performance. But the features are different importance. And the last topic, we find that, okay, the large language model simulation shows somewhat good alignment with the real world USGS deduced field map. We also found the simulation performance depends on model type, size, and input information. But at the same time, I think for my today's presentation, I just put a lot of emphasis on like large language model have a lot of potential for this spatial intelligence, but actually at the same time, we also find a lot of limitations. So for example, like for the first project, we have observed that large language model shows a lot of bias in the image geolocalization, right? Especially for those less populated areas. The performance decreased a lot compared to those populated areas. And then for the second project, although for some wildfire events, we find that, okay, by feeding the geospatial information, that can help improve the large language model prediction performance. But we also found in other events, the prediction performance is not that satisfied. So we find that the performance is actually not very consistent. And we are still trying to find some good explanation to explain why the performance vary a lot. And like for the last simulation, we also find that although the correlation might show some alignment with the real world observation, but you can observe that the absolute prediction actually could be deviated from the ground truth values, right? But the correlation is good. And the other thing we also did some analysis in our paper by trying to identify whether large language model can capture the information, like the location information. We do find that when the simulated pipeline, the agent is far from the epicenter, large language model can actually capture that information. Actually, when the distance between the simulated place and the epicenter increases, actually the simulated impact decreases. That's good. But at the same time, we also found large language model is not very sensitive to some geospatial features, such as the site condition that I mentioned, which is very important for the seismic risk prediction. But we found that large language model can actually cannot capture the relationship between the prediction values and the site conditions. So at the same time of showing the potential of large language model for the geospatial intelligence, I also want to mention their limitations by performing the geospatial tasks. And in the end, I want to share some takeaways and future opportunities. So for the first lesson that we learned from this project is that if we want large language model to have good geospatial intelligence, we really need to integrate some specialized domain knowledge. So this is like what we have shown in our second project. When feeding the proper information into the large language model, it can help enhance the large language model prediction. And the second lesson that we've learned is that we really need to come up a way to mitigate the geographic and environmental bias, especially for those maybe less resource places or areas. And the next lesson that we learn is that how to unify the heterogeneous data sources is very key. It's a very key lesson in the geospatial tasks. The reason is because geospatial data generally exist at varying scales and granularities. So bringing those diverse data sets into a unified framework is really important to enable consistent analysis. And the last point that I want to share is that we really need to make the spatial reasoning explainable. So we need a system to not just output a prediction, but output the very reasonable and a consistent reasoning process to support its prediction. And this could be very important for the downstream tasks and help the decision makers to bridge the decision-making process with the reasoning process. And so these are all the lessons that I want to share in my today's presentation. And I want to thank again for all the audience for taking time to listen to my presentation. Now I want to open the floor for questions.
Thanks so much, Neil, for the very informative talk. It's super interesting. I really learned a lot from your talks. Previously, I have not too much knowledge on this specific topic, but I feel it's super interesting and very impactful. And I do have lots of questions, but maybe we can start from some questions from our audience online.
Yes.
I guess there's one audience asking. I guess in the first of your talk, in the first work you
Yeah.
mentioned, I think you are using some large model self-reported certainty score, right?
Yes. It's confidence
Right.
score.
Yeah. So basically, I think the question is like why you choose it. Like for instance, is it reliable? Like how you design it?
Yeah, so this is a really great question because I know there are a lot of studies in large language model trying to investigate the relationship between the confidence levels and the prediction accuracy, right? So the reason is because we feel those images they have different visual cues, and some of the visual cues they're really clear. So like for example, there are like some like street signs or business names. So that can really help the model confidently output a location for its output. But for other images, like the second image, it's just like a really random image taken from anywhere in the world. So we want to use this confidence level to guide the large language model to like feel how confidently it is about its output. Because for some of the images, it's really hard to identify the vision cues. And that's the reason why we integrate the confidence level into the reverse geocoding process. And we actually find some interesting observations, like for some model like GPT 4.1, when GPT 4.1 is super confident about its output.
Mhm.
And generally, the output is correct. And when GPT 4.1 is not very confident about output, and generally those output are
Yeah.
not. Yeah, but we also find like O3 and Gemini 2.5, as I mentioned in the presentation, we find that like O3 is generally not very confident about its output. But if you compare the performance across these two models, the confidence level does not play any importance on its accuracy because the accuracy is quite close to each other. Like O3 is
Mhm.
not confident, but Gemini 2.5 is super confident, but the accuracy is pretty close. Yeah.
Yeah, super interesting. I guess we also observe similar the confidence trend in other scenarios, right? So basically,
Yeah.
it's very different across different models. That's super interesting. And also, I guess another audience is also asking, like, still in the first project, I guess
Yeah.
you are using some regression methods, right? So
Yeah.
basically, I think the question is about, is that for the baselines or what kind of thing? Could you please add more information on this part?
Yeah, this is a really great question. So the original idea, so why we build this two regression model is because we try to quantify the reasoning process. Because generally, large language model can output like a description of its reasoning, right? But it's really uncertain why large language model can do this very challenging task because the image geolocalization is not easy. It involves a lot of analysis regarding the visual cues, a lot of the environmental cues. So we are very curious to know why large language model can identify those factors and what factors if a large language model can correctly identify, that can contribute significantly to the to the success geolocation process. So that's why we build the regression models. So we can consider the why So like for the first model, we consider whether large language model can correctly identify the city level information. And then we put all of the information that large language model extract from the image at the X at the dependent features. And then we put all of the dependent features and the output feature into the regression model. And then we can calculate the coefficients and the p-value regarding each feature, regarding each input feature. So through this way, we can quantify the importance of the input feature and quantify the reasoning process. Like for example, like from the feature importance analysis, we found that when large language model can identify the street information or the urban information or the outdoor information, and then it's very likely large language model can correctly can correctly identify the geolocation from an image.
Yeah, super cool.
Yeah.
Hope this clarifies the audience online's questions. I also have some question about your first work because I think it's super interesting. But maybe my question is a little out of the scope. I'm just wondering. I'm pretty sure there's definitely some work on the trustworthiness about this geolocalization, right? Because I mean, um, like we can see the larger model has a very strong ability to do this kind of geolocalization, but I guess there maybe also have some concerns on privacy. Like if I just upload a picture of myself with some background, maybe the model can also know where I'm from. So basically, I mean, do you have any thoughts on this? Like, did you try to, or maybe there's some research on this topic. Like, is there anything to do this kind of um, preserve this kind of privacy, like not make these models to know like the exact location of a specific person.
Yeah, I think that's a really interesting topic, and thank you so much for proposing this question. And especially, I think because we just come back from the NeurIPS, I think I
Mhm,
also
mhm,
learned a lot. A lot of people they're trying to um, build some methods that make the large language model incapable of doing the things, right? Because like
mhm.
for
Yeah,
example, if we just feed the large language model a image, there are a lot of like privacy information, and we don't want large language model to learn from those private information. I would
exactly.
definitely think about how we can make large language model incapable of doing this. Yeah.
Yeah, I fully agree. Maybe this is some interesting future work because I'm also thinking about something about maybe we can also do some adversarial robustness, right? Like for
Yeah.
instance, if you put the Eiffel Tower in front of the
Yeah.
image, but the background is from another country, so will you fool the model to know like what is the location is? So maybe this is some interesting thing we could do.
Yes, I agree. Yeah, I totally agree. I feel that's a really interesting direction to explore in the future.
Cool,
Yeah.
interesting. And also like I guess maybe your second work or something you mentioned like I guess you also use LM agents to do this kind of um thing, right? Like the wildfire prediction or to have some output based on this different scenario. I'm just wondering, did you test the latency of this kind of agent? Because I guess in some cases, like it has to be react in real time, right? Like you
Yes.
cannot wait for a long time to the model to retrieve lots of things, to think a lot. So I'm just wondering how it real works. Did you test it in some real world scenarios or some systems?
Yeah, I believe in our original paper,
Yeah.
especially because we just submitted this paper and we also received some similar feedback from the reviewers. And also
Mhm.
one reviewer asked us about the latency because like exactly like
Okay.
you say, like for some disasters, it require really fast response. And
Mhm.
we add the latency and I couldn't remember the exact number, but for each case, like for each um, days prediction, I believe it just at most it just takes several, maybe like 10 seconds or 20 seconds. I can't
Okay.
remember the exact
Mhm.
number, but not that
Cool.
long. Yeah.
Cool. I got it. Got it. Then
Yeah.
that I guess that may be very useful in real world systems to do the real time reaction, I guess.
Yeah, yeah. One very interesting observation also from the second project is that we
Uh-huh.
find in some cases when feeding the large language model with different types of geospatial information, it can increase the performance. But also in a few events, especially regarding the cost prediction, we found that feeding the geospatial information can decrease the performance a little bit.
Mhm. Oh,
Yeah,
that's super
so
interesting.
yeah,
Mhm.
so we are still wondering maybe large language models still have some challenges in understanding the relationship, especially between those numerical factors.
I got it.
Yeah.
Super cool.
Yeah. Thank you so
I
much.
also
Yeah.
have yeah, super cool. Thanks for the answer. I think that's super interesting. And also, I also have some questions for your third work. I think it's
Yeah.
also very interesting. So I just wonder, like, I guess to use the retrieval augmented, right? Like
Yeah.
to retrieve from some extra knowledge. I just wondering, did you check like what kind of knowledge being retrieved? I mean, for instance, is it based on the how should I say, like the geographical property of that area, or based on some earthquake report, like some same properties of the earthquake, records. So I'm just curious about this. I have no
Yeah.
knowledge on this. Mhm.
Yeah, you are exactly correct. Actually, you get the right answer. So we build a retrieve data set. So using because for the simulated data set, so we just create a lot of like sensors across different places. And then for the retrieve data sets, we just build the sensors in other places. And then when the large language model to retrieve the information, just compare the similarity like between the site condition, the
Mhm.
distance, the population density, and also the education, the street view by compare the similarities between the simulated area and also the
Okay,
ground truth value from the retrieved data sets, and then make a prediction.
I got it. So basically, it's a fusion of this all different kinds of information, right?
Yes, and we found that actually the RAG system can significantly improve the prediction, the simulation performance.
Okay, cool. Did
Yeah.
you observe like which one of them is most being retrieved? For instance, did they mostly based on geospatial or something else? I'm not pretty sure.
Yeah, I need to check that. Yeah,
Mhm.
I need to discuss
Okay,
with
cool.
my
No worry.
another colleague. Yeah.
Yeah, no worry. And also, I also have one question about this project is that I think you are using I think you call the DYFI reports, right? So basically,
Yeah.
it's reported by a user. Like for instance, how do they feel about the scale, and how
Yes.
do they feel about the psychological panic, right? So
Yes.
I'm just wondering, how should we understand, like, if we use LLM to do this kind of simulation? I mean, um, maybe I missed some parts of your talk, but I'm just thinking, like, whether we should say we are using LLMs to simulate real physical damage, or we are just using it to simulate the humans' perceived panic, or it's
Yeah.
a combination of both. Like, I'm not
Yeah.
pretty sure.
Yeah,
Mhm.
that's another very great questions. Yeah, so basically we just simulate how the people perceive the risk. It's not real physical damage. It's not. It's
Okay.
just based on how people feel about the shaking level of the earthquake.
Mhm.
So we firstly got some ground truth values from the Did you feel map. So basically in the ground truth survey, so they provide an estimate. It's not an estimate. It's a real value reported by users who feel the earthquake. So it's an aggregated value in a region, in a zip code.
Mhm.
And we use that value reported by users, aggregated value reported by the general public at the ground truth. And then we simulate. So you can see from this conceptual framework, you can see that we just simulate a lot of human sensors in different places. And by feeding those information into the human sensors, like say, hey, I live in this place, and here are the features of my surroundings, and then there would be an earthquake happen like maybe like 200 kilometers from my place, and how would I perceive the shaking level in my current place. So this is totally simulation. This is just to simulate how people perceive the shaking level of the
I
earthquakes.
got it. I got it.
Yeah,
Super interesting.
thank you so much.
Actually, I still have lots of questions, but I think we are already on time. So maybe let me ask one more last question. So maybe it's a very high level general question. So I think you are expert in doing this kind of geospatial intelligence. I'm just thinking, like, what do you think is the most bottleneck of the current research? For instance, do you think it's because of the model lack the knowledge of understanding the physics world, or do you think is it because we do not have very high quality data to train them to learn this kind of intelligence?
Yeah, I think that's a really great question because I want to go back to my first question, like
Mhm.
the title of the presentation, right? Do large language model really have the geospatial intelligence? I feel it could go in both ways. although large language model have shown some potential, in other cases, actually, large language model also show a lot of limitations and biases. Like the one challenge, as you mentioned, is the training data, right? Especially as we
Yeah.
observed, like for the first project, like for some places, the accuracy is actually quite low. Like for this figure, right? Like
Yeah.
for those like really resource intensive places, like really densely populated area, the population, the accuracy, the performance accuracy could be quite high. But for like the middle places in the United States, you can see nearly all of the models just show really low accuracy. So I guess one of the reasons is because large language model, the training data might reflect the real world data. It's because
Yeah.
people just live in those places. So like for those like less populated area, maybe large language models performance could be really terrible. So I think this is one challenge for large language model to understand the geospatial tasks. And another challenge, I think this is not restricted to the geospatial tasks. This restrict
Mhm.
to this just apply to all of the tasks that involve in the numerical process, because we still find it also like in the geospatial tasks, large language models sometimes are also not very good at processing especially the large tabular data, because the relationship between the features could be quite complex. So large language models are not very good at processing this high dimensional features. So I feel this could be another challenge for a large language model to understand the geospatial intelligence.
Exactly. Actually, I fully agree. I think
Yeah,
this is maybe not special to this specific topic, right? So it also applies to other areas, and we see like different researchers have different solutions. So probably, I mean, large model probably is not the final solution. We still need some new architectures and new models.
yeah, I
Cool.
agree. Yeah, if the audience have more questions, please just feel comfortable to send me email and I will answer them.
Yeah, definitely. Thanks a
Yeah,
lot, Leon, for the nice sharing again, and also thanks for everybody for coming. As Leon said, if you have any questions, please email Leon, and also you can reach out to us. Thanks again. Wish you have
yeah,
a
thank you
good
so much for
weekend.
the invitation, and I hope everybody will have a great weekend.
Thank you. Bye bye.
Thank you. Bye bye.